In this section, we are going to discuss about switched capacitor circuit. That's in fourth module. It's a part 2 of fourth module. It consists of three things: implementation of resistor using switched capacitor, implementation of integrator and low pass filter or a first order filter using switched capacitor. The concept of switched capacitor is we can replace a resistor in terms of a capacitor, resistor with a capacitor and a switching clock signal. Okay, a switch and a switch, capacitor and a switch. This is a basic implementation of a resistor using capacitor. It consists of two switch, S1 and S2, and the basic requirement is the control signal or the clock signal must complement to each other. The phi 1 and phi 2 must complement to each other for implementing resistor in this manner. If we are able to implement resistor using this switched capacitor concept, then any other circuit like integrator or first order filter, or we just it is low pass filter, or integrator consists of an RC circuit. It may containing active elements. Amplifiers will be there. Amplifiers we can easily integrate in most circuit. We are not discussing now. So if we have an RC circuit or integrator, this resistor we can replace with the switched capacitor circuit. Okay. So what's the advantage of this switched capacitor? The advantage of switched capacitor is the elements like resistor and inductor. It is very difficult to fabricate resistors and inductors in integrated circuits. Integrated circuits or ICs. ICs are fabricating based on MOS technology. Most of the ICs are fabricating based on MOS technology. So in that, it is very difficult to fabricate resistors and inductors. Inductors are huge in size, and in case of resistor also, the price dimension of accurate the integration of resistor is also difficult. But if we are able to define a resistor in terms of capacitor and clock signal, it is easy to accurately define the resistance value. How an resistor can fabricate from capacitor or using capacitor, that we will discuss in the next section. Okay, so in this section here, it is a sampling circuit. Okay, it's a sampling circuit using MOSFET. Actually, I think this is not in our syllabus. Just for the understanding the working of MOSFET, we are just discussing. Okay, so here is a sampling circuit using MOSFET. So here the sampling circuit is nothing but a capacitor and a switch. So when the switch is closed, capacitor is charged. When the switch is closed, the capacitor will charge, and when switch is open, the capacitor will hold it. Capacitor will hold the signal. So it is nothing but a sample and a hold circuit. Not only sampling, it is a sample and a hold circuit. How we can implement this on using MOSFET or MOS technology? So this switch we can implement by using a MOSFET. Here it is an MOSFET, and here we are giving a control signal phi. Phi is a clock signal, square wave signal, or maybe a pulse signal. Okay, phi may be a pulse signal. Pulse signal, it having a positive and a negative signal paths are there. When this input is high, clock signal is high, not only input, the clock signal is high, this MOSFET become on and it will transfer the input signal to the capacitor, and capacitor starts charging. Okay, and when the switch is off, there is no discharge path for this capacitor. It will hold the charge, and next clock cycle, next positive half cycle, this again will happen. And when the switch is on, so we need to discuss one thing. When the switch is on, what is the resistance offered by this switch? Okay, in MOSFET, under on condition or in the saturation condition, the MOSFET resistance value is Rn is 1 by mu n CoxW by L VGS minus VT. So it's nothing but simply an RC circuit. Okay, so it has some low pass capability. Okay, and the resistance value is Rn 1 by mu n C ox W by L VGS minus VT, where the value of VGS is VDD minus Vin. VDD is from the pulse signal. So if we rewrite this one, this become VDD minus Vin minus VTH, or when the value of amplitude of Vin increases, what happened? The value of VDD minus Vin decreases, which implies the resistance value increases. So if the resistance value increases, the effective bandwidth of this circuit, bandwidth is 1 by 2 pi RC, starts decreasing. It will distort the signal. Okay, so if you use a single MOSFET as a switch, its effective resistance value depend on input voltage, and it increases with the message signal effective resistance value, and the effective bandwidth decreases, which introduce distortion in the output waveform. So if we analyze a similar circuit using PMOS, okay, here it is a PMOS. PMOS will on when this one is negative, okay, negative, and the resistance equation of PMOS is 1 by mu n COX W by L Vin minus Vp. Or the Vin increases, the effective resistance of PMOS starts decreasing. Okay, so here the actually the control signal is complement. Okay, complement also. So Vin increases, the effective resistance of RP, effective resistance of PMOS, but decreases. So if we draw the resistance characteristics 0 to infinity, the Rn, the resistance value of NMOS increases with the resistor input signal Vin, and the effective resistance of PMOS decreases with the Vin. So if we connect these two are in parallel, Rn and Rp in parallel, this will be the effective resistance value. This will be the effective resistance value Rn parallel to Rp. So to solve the distortion problem in PMOS and NMOS switch, we are using complementary MOSFET switch. Complementary MOSFET switch use both the PMOS and NMOS. Here it use NMOS here, PMOS here, and the control signal are phi and a minus phi. During positive half cycle of the signal, this will be on as well as this will be on due to the negative half on phi dash. So both the signal are short circuited and input is passed to the output, and effective input resistance is Rp parallel to Rn, which is a constant value, almost constant, and it is a low value. So which will give higher bandwidth for this sample and hold the circuit. Okay. Actually, this is not specified in syllabus. If they ask explain the working of MOSFET as a switch, you can explain this one, or as a sample and hold circuit, you can explain this one. Next, we are going to discuss implementation of resistor using switched capacitor. Okay, so here we have drawn an equivalence resistance equivalent of a capacitor, or implementation of resistor using capacitor, and this circuit is called parallel switched capacitor because the capacitor is connected parallel to the voltages. Okay, so okay, fine, the capacitor is connected to parallel to the voltages, and to evaluate the equivalency between these two circuits, we are assuming that V1 of t here, V1 of t and V2 of t. Okay, first I will take that. V1 of t and V2 of t is nearly constant during our pulse duration or the time duration of phi1. So implementing switched capacitor, we are using a capacitor C and two switches S1 and S2. This we can implement using MOSFET. Okay, NMOS you can use to implement this one, and here you will give phi1. Okay, to use two clock signal phi1 and phi2 with the period t. And the property of phi1 and phi2, it is non-overlapping. Okay, non-overlapping, and one more condition is there. The width of the individual clock is slightly less than t by 2. That means if phi 1 is like this, we are implementing phi 1 like this, where this is t, its own period is t1, that t1 is less than t by 2, and phi 2 is designed like its also time period is t, and it also satisfies this t1 is less than t by 2, and these are not overlapping. Okay, the on time must be less than off time in both phi 1 and phi 2. And another condition is, we are assuming that during this time period, one time period duration, we are assuming that the v1 of t and v2 of t are constant. So we can write it as v1 and v2 here itself, v1 and v2. If it is v1 and v2, the terminal voltages are v1 and v2, we will get the current through this resistor R, I1 of t or I, is equal to v1 minus v2 by R. And we are trying to find the value of I1 of t in this circuit. Then we will relate these two quantity and we will find the effective resistance value. So here I am going. So to evaluate current through this one, this current I1 of t, we are trying to express in terms of charge in capacitor C. So current through in the capacitor, I1 is the average current. Okay, it's an average current. Average current is nothing but 1 by t integral 0 t I of t dt, and the current we can express in terms of charge. Okay, dq by dt, or it is nothing but this integral become q of t by 2 minus q1 of 0, because in that time period, in the phi, in clock phi, we have the clock signal, active clock signal only up to duration t by 2 or t1 dash or t1, which is less than t by 2. So the average current 1 by t q1 of t by 2 minus q1 of 0. So charge stored in the capacitor at a t by 2 and at a 0. What's the charge stored at t by 2 is what voltage we applied. If we apply V1, charge stored by capacitor C become CV1. Okay, before that means before applying this phi 1, before switching on this one, this capacitor is connected to here, right? V2, here it is V2. So charge at a zeroth instant is CV2, or this will be the Q0. This will be the Q0. So the value of I, that is 1 by t q1 of t by 2 minus q1 of 0 is become cv1 minus cv2, or we can write it is I is c by t v1 minus v2, and the value equating the average current and the actual current through the resistor, we will get the value of resistor is t by c. Okay, so using or defining the value of c and the time period of clock, we can accurately define the actual value of resistor that we want into the circuit. Okay, that's all. And earlier case we said it is a parallel switched capacitor resistor. Here is an example of series switched capacitor equivalent of resistor. Here the capacitor is connected in series. Here also the equivalent value R equal to t by c, R equal to t by c. There are some other implementations also there. You can look into that in textbook. Okay, so here the capacitor is connected in series, and serial parallel combination is also there, and on bilateral combination also there. You can just go through the figure, that's enough. Derivation is not required. Derivation of this one, parallel switched capacitor or parallel switched capacitor resistor is important. Okay, and next we are trying to implement low pass filter using switched capacitor. So just we implemented a resistor using capacitor and two switches, okay, two non-overlapping switches with the clock signal, non-overlapping clock signal switches, okay. Here we need to implement a low pass filter. Implementation is low pass filter in general case analog circuits. We know it is simply an RC circuit. RC circuit will act as a, if we take output from here, output from here, you will get a low pass response. So now here we are trying to implement a switched capacitor filter or a digital filter. How we can implement a digital filter? Digital filter because we are operating on sampled signals. Okay, so switched capacitor filter. So switched capacitor filter, we are implementing that resistor using a simple switched capacitor, and so this R1 is replaced with a switched capacitor C1 and two switches S1 and S2. You can also replace these switches with the MOSFET, okay, and it use phi 1 and phi 2, two clock signal, and phi 1 and phi 2 are the same definition, non overlapping clocks, period T, and one more condition is there, T on must less than T by 2. Both the case, T on of phi 1 and phi 2 is less than T by 2. Okay, the value of resistor R1 we need to implement is R1 is T by C. So now we are trying to verify is this circuit will act as a low pass filter, or the transfer function of this low pass filter is, or this circuit transfer function of this circuit is same as that of a low pass filter. To derive that, we are considering, to derive the transfer function, we are considering a clock phase, and we are assuming the signal is starting from n-1t. Okay, from n-1t we are applying a clock signal phi 1, and then we will apply next half cycle, we will apply phi 2, and in nt we will apply phi 1, and then we will apply phi 2, etc. And we need to verify how the voltage across C1 vary with respect to the input signal, and how C2 vary with respect to charges in C1. In the first half, Q1 is on, then the C1 receive charges from V1, and in the next phi 2 is on, C2 discharge that charge to C2, or they will discharge each other, C1 and C2. Okay, so that's the basic idea. So here the voltage across this one is V2, voltage across this one is V2, here we will assume it is V1, and it is V1 of t because it is varying with respect to time. So first we are starting with an idea. The phi 1 is on, and the time period is from n-1t to n-1/2 t. This time period is taken for the easiness of derivation of transfer function. So here the input is connected to C1, and C2 is isolated because phi 2 is no off, right? Phi 2 off. So C2 hold its charge. There is no discharge path for C2 here in this circuit. There is no discharge path when phi 2 is open. So the C2 will hold that charge. Okay, and assume C1 is charges. Now C1 is charges from Vin, and it is charges from Vn minus 1 of t, or V1 of n minus t is equal to Vin of n minus 1 t. Okay, and C2 remain in the previous charge itself at the time of n minus 3 by 2 t, or the, we know, as per the clock cycle, the charging of T2 or variation of C2 take place when the phi 2 is on, or in the period of n minus 1 by 2, n minus 3 by 2, n plus 1 by 2, n plus 3 by 2, etc. Okay, so here charge in C2 remains same as that of charge at n minus 3 by 2, even this Q1 is on. So here charge at V2 remain at n minus 3 by 2 even at n minus 1 of t. Okay, and we can draw an equivalent circuit of this one. When the switch is closed here, input is V1 of n minus 1t is given to the circuit, and here the capacitor C2 hold a charge. C1 is not holding any charge because it discharges to C2 in the previous 5-2 cycle. Okay, 5-2 cycle അത് discharge ചെയ്തു. So when C2, it hold a charge V2 of n minus 3 by 2 into t, even at n minus 1 t. So this is an equivalent circuit. Here we are representing the capacitor with an ideal capacitor. The capacitor voltage of Vc1 equal to 0, and here Vc2 equal to 0, and capacitor with the voltage, the capacitor and a voltage supply is represented. Okay, here the same representation, here we split into a voltage source and a capacitor. Okay, fine. So what happened in next half cycle? During the next half cycle, phi 2 is on and phi 1 is off. So that time this will be connected. The capacitor C1 will supply charge to C2. Capacitor C1 have a charge that is V1 of n minus 1 t that will supply to C2. Okay, so at next half cycle from t equal to n minus 1 by 2 t to t equal to nt, the capacitor C1 already hold a charge V2 of n minus 1, and we are supplying an additional charge that is V1 of n minus 1, and these two together we will get a output voltage that V2 of n minus 1 by 2 t, because the voltage at the capacitor C2 change n minus 1 by 2, n plus 1 by 2, n plus 3 by 2, etc. that interval. Okay, so V2 n minus 1 by 2 we will get, and we need to calculate the actual voltage from this one using superposition principle. Using superposition principle, from this voltage it will split between C1 and C2, and this voltage also split between C1 and C2. So we will get V2 of n minus 2t is equal to C1 into C1 divided by C1 plus C2, C1 divided by C1 plus C2 into V1 of n minus t. Because here the capacitor is there, if we consider this voltage source V of n minus 1 into t, voltage across C2, voltage across capacitor C2, ZC2 divided by ZC1 plus ZC2, it's become C1 divided by C1 plus C2. Okay, C1 divided by C1 plus C2 into that voltage. Okay, that voltage V. So see, here it is V1 of n minus 1t. Okay, it's split into like this V. So here it is C1 divided by C1 plus C2 into V1 n minus 1t. Due to V2, it's split into C2 by C1 plus C2 into V2 of n minus t, and this will be same as that of V2 of n minus 1t, because voltage across capacitor C2 cannot vary in this duration. It will be same from n minus 1 by 2 to n minus 1. So these two are same. From this equation we can derive the transfer function of this low pass filter. Okay, so we just did the circuit, analyze the circuit, what happened in the first half cycle and in second half cycle. First half cycle, capacitor C1 charges and capacitor C2 hold its charge. Okay, and its charge is indicated in n minus 3 by 2. Okay, in the one of the odd half, and this is representation, split representation. And in the next half cycle, what happened? C1 will discharge that voltage to C2 and C2 charge from that one, and the actual voltage equation looks like this. And what is the transfer function of this one? So this will be the output voltage. Okay, V2 will be the output voltage, and we know V1 is the input voltage that be given to the capacitor C1. So in the next we can derive transfer function from this one. Transfer function from this one using Z transform. V of n minus n0 t is Z raised to n0 t minus n0 t into V of Z. So this transfer function, this time domain representation will changes to in frequency domain. V2 of Z is C1 by C1 plus C2 Z inverse of V1 of Z, C2 by C1 plus C2 Z inverse of V2 of Z, and rearranging this one will get V2 by V1 or HZ is nothing but C1 by C1 plus C2 Z inverse divided by 1 minus C2 by C1 plus C2 Z inverse. And if we rearrange this one, we will get something like Z inverse divided by H of Z. This H of Z is something like Z inverse divided by 1 plus C2 by C1 minus C2 by C1 of Z inverse. Or if we replace C2 by C1 into alpha, it's become Z inverse by 1 plus alpha minus alpha Z inverse, which is similar to the low pass transfer function Z inverse divided by 1 minus A Z inverse. So this circuit will act as a low pass filter. So we converted a normal analog low pass filter into a switched circuit low pass filter, or it is a digital low pass filter. Okay, it's operating on sampled signal or digital signal. And that's all about switched capacitor low pass filter. Similarly, we need to implement one more quantity like switched capacitor integrator also. Switched capacitor integrator, that I will take in the next session.